Welcome to the 10th module of Power System Operations e-learning course under the Mission Karmayogi initiative. Please note, this course uses narration, so remember to turn on your speakers or headphones while taking the course. You can also view the course transcript by clicking the Notes button above. Click Start button to proceed further. Upon completion of this module, you will be able to describe the major concepts that drive the power system stability. Explain angular stability, steady-state stability, transient stability, and dynamic stability. Summarize low-frequency oscillation and its characteristics. Understand voltage stability, voltage collapse, and voltage instability. Identify the stability assessment tools. Let us begin the module with an introduction to power system stability. The power system is one of the largest man-made dynamic systems. It couples a rotating mechanical system, an inverter-based system, and an electromagnetic system. One such coupling of an electrical and mechanical system is shown here with the example of a hydropower plant in the given figure. Thus, power system stability refers to maintaining equilibrium between all these systems. The power system stability is monitored through various parameters and their limits which indicate its overall health. Now let us learn how big the stability aspect is when the Indian power system is being described. In the Indian power system, thousands of generators, kilometers of transmission and distribution lines, and millions of loads are connected with each other. All these are connected at various voltage levels and run in synchronism with each other. This reflects the wide aspect of stability for entire Indian power system. Do you remember the grid parameters of a power system that we have learned in the previous module?
Yes, sir. The major grid parameters in any electrical system are voltage, current, power angle or load angle, active power, and reactive power.
You are absolutely correct. Let us now see how the grid parameters determine the health of a power system. The grid parameters that define the power system stability such as voltage, current, frequency, active and reactive power, and angle are like the human body's vital signs, which are body temperature, pulse rate, respiration rate, and blood pressure. Each grid parameter defining stability has its own limits defined during the power system planning stage. The power system is considered stable if all the coupled systems run in unison and the grid parameters are within the defined limits. In our day-to-day life, we observe many dynamic systems that operate with stability. These systems have one driving force and another opposing force and are stable if they are in equilibrium. A few examples of stable and unstable systems with respect to gravitational force are shown here. In a power system, we have power generation from power plants and power consumption through loads. Generators convert various other energy forms to electromagnetic energy. We simply call it electrical energy. This electrical energy is consumed by loads by converting it to other energy forms like light, heat, kinetic energy, etc. Thus, there are two opposing systems, and it is stable if they are in equilibrium. During operation, stability is ensured in a normal as well as a disturbance state. The system is considered stable if the power generated is equal to the power consumed by loads and system losses. It requires that grid parameters are within their limits and all the elements are synchronized. Now let us understand some major concepts that drive the power system stability. The first concept is called the power transfer equation. It decides the steady-state stability of the power system. it provides the input to the system operator and checks how much maximum active power, that is, watts, can be transferred from one substation or power plant to another substation or load through connecting wires. Maximum active power transfer is decided by voltage of connected nodes, impedance of the connecting wires, and power angle between connected nodes. This equation can be represented as a power angle curve and provides a steady-state stability limit. System operator monitor these angles for system stability. The second concept is the swing equation, which decides the dynamic nature of the power system stability. The power system has two kinds of torques and associated power that are in equilibrium. The first is the mechanical power, which basically represent the generation coming from the mechanical rotating turbine, coal, gas, nuclear, and hydro plants. On the other side, it has electrical power, which is basically the power generated by the generator and consumed by the load. These two torques get coupled in the power system through the turbine generator shaft and oppose each other. For the stability of the power system, these should be equal, otherwise will result in instability. During any disturbance, there will be variations in these power. The electrical power can change with load change or fault in the electrical system, while mechanical change can be due to turbine tripping or a change in input fuel rate. This change can result in either excess of either torque. The imbalance will result in acceleration torque between coupled systems and should be in limit for stability. The last concept is about two components of the electrical torque, which are synchronizing torque and damping torque. Synchronizing torque helps all the rotating systems to remain in synchronism, while damping torque damps any variation in grid parameters during the disturbance. Thus, if both are adequate, the power system ride through any disturbance. However, if any of the torques gets reduced, it can cause instability. Let's check your understanding. Select the correct option. Did you understand the major concepts that drive the power system stability learnt in the last few slides?
Yes, sir. It was interesting to learn about the various concepts.
Okay, then let us move on to the classification of power system stability. Power system stability can be categorized into angular stability, frequency stability, and voltage stability. While angular stability can be subdivided into steady-state stability, transient stability, and dynamic stability, voltage stability can be subdivided into large and small disturbance-based voltage stability. We will learn about the details of angular and voltage stability in this course. In this section, we will learn about angular stability. Angular stability in a power system refers to maintaining the power angle within a stable regime during a normal and a disturbance state of the power system. Navigate the left or right arrow to learn more. We have learned earlier in this module that the power angle between substations decides the power flow pattern. The angle will change when there is a relative acceleration in the power system due to changes in load, generation, network connectivity, etc. Relative acceleration can result in a slow change in angle that represents steady-state stability and a fast change in angle that corresponds to dynamic and transient stability. Angular stability is defined as the power system's ability to restore the power angle within stable limits after any change. The system operators should have good control over it to maintain stability. Now let us learn about steady-state stability. If power system can withstand small incremental changes in angle without losing any part of the system, it has steady-state angular stability. All grid parameters will be in the operating range. This can be seen in the given example. Remember the maximum power transfer equation we learned earlier. A generator is supplying power to load via a transmission line. If the initial load is 80 megawatts, the angle between the load and the generating plant is 30 degrees. If we increase the load as well as the generation slowly, then the power angle will keep on increasing and will reach P maximum value, which is 160 megawatts at 90 degrees. After this, no more power can be transferred if we increase the load. After this, system would not have the capability to transfer more power, and any higher power will reduce synchronizing force and cause steady-state angular instability. Thus, the operator keeps the angular separation between two adjacent substations within 30 degrees for safe operation. For steady-state angular stability, stability margin is defined as a margin available between the maximum angle, that is 90 degrees, and the actual operating angle. For a stable operation, this margin is maintained, and if it's breached, then the system moves towards instability. Now the big question is how the steady-state stability in the power system can be improved. Based on the power angle equation, it is evident that more power can be transferred if we can change the parameters on which this maximum power transfer is dependent. Let us now look at the steps that would help in maintaining the stability margin in the system. Click on each tab to learn more. The first step is voltage improvement, which can be done by improving generating end, transmission end and load end voltages. The second step is by increasing more transmission lines between the generator area and load area, which reduces impedance. The third step can be meeting load's local generation plant near to load. This will reduce dependency on long power transfer, causing low angle. The last step is controlling the power angle. It can be done through an HVDC transmission system. One important aspect is that the operator should have sufficient time to take these steps to improve the stability. Now let us learn about the transient stability in power systems. Power systems experience large change in form of a large unit or load tripping or fault in the power system. Power system fault is the addition of an unwanted path in the wires due to which current and active power flow gets disrupted. An example of fault is trees coming in contact with the wire leading to its grounding. Disruption of power from a generator to a load due to fault results in relative acceleration of power plants. The angle of the power plant will change rapidly and can destabilize them, and that is why it is called transient stability. The severity of the transient type of event can be understood by the fact that these have a high impact on the system during a small period of time ranging in milliseconds. Such event causes a significant change in the power system's behavior and does not provide any manual intervention for control. All control actions that operate are automatic. However, if such automatic control actions are not sufficient, it will move the system to instability. One example is shown here where the fault is on the line connecting the power plant. We see here how the power angle is varying quickly. During a fault, the generator accelerates and its angle can go beyond 90 degrees. After fault clearance, it will have a path to send active power to decelerate and stabilize. However, if a fault does not get cleared immediately, it will lead to higher acceleration and large angle, and post-fault may not stabilize, causing transient instability. Thus, it is important that faults are cleared as fast as possible. How important is transient stability in a power system can be understood with the two examples. The first is the power plant outage of Coastal Gujarat Power Plant, CGPL, UMPP, having a 5 into 800 megawatts capacity. The plant blackout was due to delayed fault clearance on transmission lines and causing the generator to go out of step and trip. The second example is the system-wide blackout which occurred on 30th and 31st July 2012. Here, tripping of 400 kV Gwalior-Agra double circuit between northern and western regional grids led to transient instability due to an increase in the angular separation between the regional grids. There are various measures taken during long-term planning and operational planning which can help in improving transient stability. Let's check your understanding. Select the correct option. In this section, we will learn about another aspect of angular stability, which is called dynamic or oscillatory stability. The power system at present is dominated by an electromechanical system in the form of a synchronous rotating generator and a synchronous and induction rotating load. Thus, it inherently has oscillatory characteristics similar to the spring mass system. With small changes in the power system like the loss of load, tripping of lines, etc., the system parameters oscillate and stabilize due to good damping. Good damping in a power system requires adequate damping torque in the system. In a spring mass system, such damping comes from air and surface friction which opposes such oscillation and dissipates the oscillatory energy. Similarly, the power system has natural damping in the form of resistance loss, friction loss of rotating mass, load damping, and resistance from system inertia. Additional damping in form of forced damping is also provided by tuning various controllers. The oscillations due to an electromechanically coupled system are also called electromechanical oscillations. These oscillations frequency is in the range of 0.2 Hz to 3 Hz which is low compared to the nominal frequency. Thus, they are also called low-frequency oscillations or LFOs. You can see what an LFO in a power system will look like if it occurs when superimposed over nominal frequency. LFOs are classified based on how many generators are oscillating. It is an exchange of energy between two systems. So, there will always be another group of generators that will exchange this energy and oscillate in an opposite direction from the original group. These modes can be classified further as local and global modes. Now let us learn about the impact of low-frequency oscillation. Oscillation will cause power system parameter oscillation and variation. If the variation is high, that is, oscillation is severe with lesser damping, it can result in equipment protection operations that are based on the various power system parameters. These can limit power flow at the local as well the interregional levels. Furthermore, such oscillation in a plant will cause wear and tear and directly affect its life cycle. An example can be seen here in the plot where one ultra-mega power plant UMPP, which was generating 3800 megawatts, varied from 3400 megawatts to 4200 megawatts, that is, 800 megawatts variation within a few seconds on a periodical basis. If these oscillations are not controlled, they can also result in a wide-scale blackout. Blackout due to dynamic stability issues had occurred in China, the USA, and Italy. The solution for improving dynamic stability is to improve the damping torques in the power system. It can be done by tuning power plant control. One example is shown here where oscillation can be seen in the power plant output before and after the tuning of its controller. Other methods of damping improvement are operation within transfer limits, isolation of faulty equipment or plant, reducing transmission line flows having high oscillation, strong transmission connectivity, and maintaining angle within stability limits. Do you know what voltage stability is?
No, sir.
Okay, then let us learn about voltage stability now.
Okay, sir.
You already have learned about the importance of voltage in the power system in the previous modules. In basic terms, voltage is the pressure that pushes the electrons, which carry electricity through the conduction media, that is, power lines. Analogously, voltage can be understood in terms of pressure in the hosepipe used for water supply to your garden. If the voltage is low in the power system, the connected equipment will not operate properly or may not operate at all. It is like watering plants with a low-pressure water supply through which a trickle would only come out. If the voltage is too high, it can damage the equipment. It is similar to watering plants with high water pressure leading to damage to plants. The power system is planned to operate within a range of voltages and has defined operational limits. The voltage stability is thus the ability of the power system to maintain steady-state acceptable voltages at all buses under normal operating conditions and after being subject to an event. Voltage is maintained by a reactive power balance between the source of the power and the load. Such reactive power source is generating unit. Shunt reactive devices like capacitor and reactor banks. And dynamic reactive power devices like STATCOM and SVC, load, etc. Based on the maximum power equation, it can be observed that for supplying adequate power, the voltage of the source, that is, the generator, and the voltage of the sink, that is, the load, have to be maintained. If the load increases, then the voltage will reduce in the power system. To send adequate power from the source, there will be a need to infuse reactive power. Similarly, if the load reduces, the voltage will increase, and to control the voltage there will be a need to withdraw the reactive power. Let us now understand the voltage stability by means of how voltage instability, that is, voltage collapse, occurs in the system to cause a blackout. One battery bank or generator is supplying power to various connected loads through transmission lines. The generating unit power with voltage and voltage between source and sink is shown through two curves. It can be observed that when a load is being switched on one by one due to the increasing length of wires, the voltage at the load end reduces. It reaches a point when the generator can no longer supply additional loads due to very low voltage in absence of reactive power support. This results in a blackout. The solution to avoid voltage instability or collapse is to have adequate voltage support in the form of reactive power devices. In the previous example, if an adequate capacitor bank is installed in the transmission network near to load, the voltage drop will reduce and the system will remain stable. This is visible in the associated figure. The voltage instability impacts the power system in the form of voltage collapse causing a blackout and low voltage at load leading to its wear and tear. It can further result in other types of instability like angular instability. The solution, as explained earlier, is to have adequate reactive power resources in the transmission and distribution system. This will include a reactor and capacitor. The impact of reactor and capacitor switching is shown in the given figure. Transformer tap change also helps in voltage control. Other methods are under voltage load shedding, which trips the nearby low voltage node to improve the voltage. The last one is dynamic devices like STATCOM and SVC, which can inject as well as absorb reactive power within milliseconds, thus improving stability during faults. Now, we will learn about stability assessment tools used in the power system. There are basically four types of stability assessment tools available in the control center. SCADA system, dynamic security assessment, wide area monitoring system, offline system study. Click on each tab to learn more. The SCADA system provides the power system parameters visualization of a grid with data update every 4 to 15 seconds period. It also provides breaker and isolator operations indicating whether any power system element is in service or out of service. Further, it has a tool like a state estimation, which helps the operator in stability assessment. The dynamic security assessment is also called DSA, which takes data from the SCADA state estimator and PMUs. It provides transient voltage and dynamic stability assessments. It has been recently implemented at an LDC and subsequently planned to be installed at all RLDCs. The third tool is the Wide Area Measurement System, which is a very popular tool for assessing system dynamic performance. This tool provides system-wide visibility with high resolution and time-synchronized data from various substations. The system operator can analyze the dynamic behavior of the power system. One of the largest WAMS projects is deployed in the Indian grid. The last tool that we will discuss is an offline system study. It involves software where the power system is mathematically modeled. It provides the basis for operational planning measures for future scenarios. The system operator uses software like PSSE and other software to perform activities like power flow limit study, outage study, and contingency study. Let's check your understanding. Select the correct option. You have reached the end of this module. I hope you must have understood power system stability.
Yes, sir. It was a great learning experience.
Let us quickly summarize the major takeaways of the module. The grid parameters that define the power system stability are voltage, current, frequency, active and reactive power, and angle. The overall power system stability can be categorized into angular stability, frequency stability, dynamic stability, and voltage stability. If the voltage is too low in the power system, the connected equipment will operate poorly or may not operate. If the voltage is too high, it can damage the equipment. The 4 types of stability assessment tools available in the control center are SCADA system, dynamic security assessment, offline system study, and wide area monitoring system.